Before we move ahead, let us start with understanding the classical phase space of a harmonic oscillator. And we will use this to understand what is called as the um, Wigner functions, as well as the phase space for the uh, quantum harmonic oscillator. This phase space picture is very useful when we do continuous variable quantum computing. It is just similar to the block sphere picture that we study when we do discrete variable quantum computing. So, this phase space picture gives you a good idea of a graphical representation of how things are moving around in the continuous variable quantum computing scenario. So, let us start with the classical harmonic oscillator. So the classical harmonic oscillator, simple harmonic oscillator, its equation of motion is given by this equation, where this m omega square is also called as k. And if I draw a picture of this classical harmonic oscillator, you can think of it in this way, where we have a block attached to a spring, or let's attach it this way, and we give a push to it and it will oscillate up and down over time. This is the center of mass of that block. Now, the solution to this equation of motion is given as x, which is dependent on time, which is x0 cos of omega t plus phi, and the momentum, which is given as mv, that is m dx by dt, is equal to minus x0 m omega sine of omega t plus phi, where phi is the phase at which the it starts. Now, if I try to convert this into a dimensionless form, these x and p, then it is given as x by x0, and p tilde is given as p by m omega x0. This is the dimensionless form of the solutions. So if I create a space where the x value is on the x-axis and p value is on the y-axis, then I can create a then I name this kind of a space as a phase space. And this is what phase space is. And phase space is a good way to visualize how the dynamics occur inside a particular system. So if I plot this phase space, the points of the harmonic oscillator, then I would see that this x and p will be some dot on this particular circle x tilde at time t, p tilde at time t, and this will give you x tilde at time t and p tilde at time t. And this particular dot will move in this manner with a frequency omega. So this is how the phase space will look. So as this harmonic oscillator, its position x tilde, let's say, will oscillate up and down, this point will keep on moving in this count in this clockwise rotation in this phase space.